A small, icy moon barely wider than the length of Arizona is spraying its own subsurface ocean directly into space, and scientists digging through those samples have now checked off nearly every single item on the basic chemical checklist required for life. Not most of it, nearly all of it. Stick around, because I'm going to walk you through exactly what researchers have found inside the plumes of Saturn's moon Enceladus, why the most recent additions to that list are considered especially significant, and why scientists still won't call this confirmed evidence of life, no matter how complete the picture is starting to look. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the search for habitable worlds in our own solar system. To understand why Enceladus generates this much scientific excitement, you first need to understand what makes it such an unusually convenient target for this kind of research in the first place. Enceladus is a small moon of Saturn, only about 300 miles across, encased in a thick shell of ice. Beneath that shell sits a genuine global liquid water ocean, kept from freezing solid by internal heat generated through tidal flexing, the same gravitational squeezing and stretching Saturn's gravity exerts on the moon as it orbits. That alone would make Enceladus scientifically interesting. What makes it exceptional is what happens at its south pole, where a series of long fissures nicknamed tiger stripes allow water from that buried ocean to erupt directly into space, as towering geysers, some jets reaching hundreds of miles above the surface. Some of that ejected material falls back down as fresh snow. Some of it escapes the moon's weak gravity entirely and goes on to form Saturn's E-ring, a faint, diffuse ring of icy particles that circles the planet well beyond its brighter, more famous main rings. That geological quirk turned Enceladus from an obscure, unremarkable snowball into one of the most accessible ocean worlds in the entire solar system, for one simple reason. Scientists don't need to drill through miles of ice to sample its interior. The moon is doing that sampling work for them, launching fragments of its own ocean directly into the path of any passing spacecraft. NASA's Cassini mission, which orbited Saturn from 2004 until it was deliberately destroyed in the planet's atmosphere in 2017, took full advantage of that opportunity, flying directly through Enceladus's plume and through the E-ring itself on multiple occasions, using onboard instruments to directly analyze the composition of the icy grains it passed through. It's worth appreciating just how much of a lucky accident this entire research program actually is. Cassini wasn't originally sent to Saturn with Enceladus as a primary target at all. The mission's early planning focused overwhelmingly on Saturn itself, its rings, and its largest moon Titan, with Enceladus treated as a comparatively minor stop along the way. It was only after Cassini's first close flyby in 2005 revealed the unexpected plumes venting from the moon's south pole that mission planners scrambled to redesign later portions of the spacecraft's trajectory specifically to fly back through that plume repeatedly, turning what had been a minor waypoint into one of the mission's signature scientific achievements. Every discovery discussed in this video traces back to that mid-mission course correction, a reminder that some of the most significant findings in planetary science emerged not from the original plan, but from a mission's willingness to adapt once reality turns out to be stranger and more interesting than anyone expected going in. If you're finding this as exciting as the researchers involved clearly are, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. To understand why researchers care so much about cataloging specific chemicals here, it helps to know what scientists actually look for when assessing whether any environment, anywhere, could plausibly support life. Habitability. Researchers generally focus on a short list of core requirements. Liquid water, a source of the essential elements. Life is built from, commonly summarized by the acronym CNOPS, standing for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and a usable source of chemical energy that organisms could actually metabolize. Enceladus had already confirmed the liquid water requirement convincingly by the time Cassini's mission ended. The plume itself is direct, physical proof of a subsurface ocean. The remaining question has been whether the rest of that checklist could also be satisfied, and piece by piece, follow-up analysis of Cassini's archived data has continued filling in gaps that seemed genuinely uncertain even a few years ago. The earliest major piece of that puzzle came from a straightforward but crucial detection: molecular hydrogen, confirmed in the plume back in 2017. Hydrogen coexisting with carbon dioxide in roughly the right proportions strongly suggested the availability of chemical energy that could support a specific kind of microbial metabolism called methanogenesis, a process in which simple single-celled organisms combine hydrogen and carbon dioxide to produce methane as a byproduct, releasing usable energy in the process. Methanogenesis is genuinely ancient and widespread here on Earth, found in extreme environments ranging from deep-sea hydrothermal vents to the digestive tracts of livestock, and its potential availability on Enceladus meant researchers had found not just raw ingredients, but a plausible actual mechanism by which simple life could theoretically sustain itself using nothing but chemistry already confirmed to exist in that buried ocean. The next major addition came in December of 2023, when a research team led by Jonah Peter, a doctoral student at Harvard University working alongside colleagues at NASA's Jet Propulsion Laboratory, published a detailed reanalysis of Cassini's plume data in the journal Nature Astronomy, using an improved statistical framework. Capable of untangling previously ambiguous overlapping chemical signals, the team confirmed the presence of hydrogen cyanide in the plume, along with several other organic compounds. Peter has described hydrogen cyanide as something like the Swiss Army knife of amino acid precursors, since its molecular structure allows it to be assembled in many different combinations to form various amino acids, the basic building blocks that link together to form proteins in every living organism on Earth. According to Peter, the strength of that specific detection only became more convincing the harder his team tried to find alternative explanations for the data, eventually concluding there was no way to properly match the plume's chemical signature without including hydrogen cyanide as a genuine component. Phosphorus turned out to be the most stubborn item on that checklist, and its eventual confirmation came through one of the more roundabout scientific stories in this entire body of research. Earlier geochemical modeling, published in 2022 by a team including Southwest Research Institute scientist Christopher Glein, predicted that phosphorus should theoretically be abundant in Enceladus's ocean, based purely on the underlying chemistry of the moon's rocky seafloor interacting with its overlying water. That was a prediction, not a direct detection. And phosphorus specifically mattered because, on Earth, it's often the single limiting nutrient that caps how much biological activity an ecosystem can actually support, essential for building DNA, RNA, cell membranes, and the energy-carrying molecules every known form of life depends on. In June of 2023, a separate international team led by researchers at the Freie Universität Berlin went looking for direct physical confirmation of that prediction, reanalyzing archived Cassini data specifically from the small subset of salt-rich ice grains it had sampled while flying through Saturn's E-ring. They found it. High concentrations of sodium phosphates turned up in those grains, and follow-up laboratory experiments modeling Enceladus-like ocean chemistry suggested the moon's actual phosphorus concentration could run at least 100 times higher than what's found in Earth's own oceans. That leaves sulfur as the most recent piece of this puzzle to fall into place, and it's the specific addition that's generated the most attention within just the past couple of years. Hydrogen sulfide, the same compound responsible for the smell of rotten eggs, had actually been tentatively flagged in Cassini's raw plume data going all the way back to its original 2009 flyby measurements. But the spacecraft's mass spectrometers simply didn't have the resolution needed to distinguish it confidently from other molecules with a similar mass, leaving its presence genuinely ambiguous for well over a decade. More recent modeling work, published in the Astrophysical Journal Letters, has revisited that ambiguous signal alongside everything else now confirmed in the plume, and concluded that Enceladus's ocean likely contains enough sulfur and dissolved iron, combined with the previously confirmed phosphorus, to be considered fully habitable by the standard chemical definition researchers use to evaluate potential life-supporting environments. Sulfur matters specifically because it hints at active geothermal processes happening at Enceladus's rocky seafloor. And here on Earth, the deep ocean hydrothermal vents that release hydrogen sulfide happen to host some of the most extreme and resilient forms of microbial life ever discovered, organisms that thrive in complete darkness using chemical energy rather than sunlight. It's worth being genuinely careful and precise about what this growing list actually proves, because it's easy for a story like this one to drift into overstatement if you're not careful with the language. Every one of these confirmed chemicals, hydrogen, hydrogen cyanide, phosphorus, and now sulfur, establishes that a specific ingredient necessary for life is present and available in Enceladus's ocean. None of them, individually or combined, constitutes direct evidence that life actually exists there. Jonah Peter has been explicit about this distinction in discussing his own team's hydrogen cyanide findings, framing the result as evidence that Enceladus meets the basic requirements for habitability, and that researchers now have a clearer idea of how complex biomolecules could theoretically form there. Language carefully chosen to describe potential rather than confirmation. Every one of the researchers involved in this broader body of work has been similarly careful, and it's a distinction worth respecting rather than glossing over for the sake of a punchier headline. There's also a specific limitation baked into how this entire research program works that's worth understanding, because it shapes what scientists can and can't say with confidence at this stage. Every detection discussed here came from remote, indirect analysis, ice grains and gas molecules captured by a flyby spacecraft traveling at high speed, rather than a laboratory sample, collected and studied directly on Enceladus's surface or within its ocean. Cassini's instruments were also never specifically designed to hunt for biosignatures in the first place, meaning researchers have spent years essentially reanalyzing data collected for other scientific purposes. Squeezing additional insight out of an archived data set, the original mission never intended as its primary focus. That's part of why Peter has specifically pointed toward laboratory experiments as a logical next step, proposing that scientists could recreate Enceladus-like ocean conditions here on Earth in a controlled setting, sometimes described informally as a mini Enceladus, to directly test whether the specific combination of molecules already confirmed in the plume could actually assemble into more complex biomolecules under the right conditions, rather than simply sitting present but chemically inert. That limitation is also precisely why the idea of an actual return mission to Enceladus has generated so much sustained interest within the planetary science community. A future spacecraft carrying instruments specifically designed to search for biosignatures, rather than repurposed general chemistry instruments built decades ago for an entirely different mission, could fly through this plume with the specific, targeted question already in mind, dramatically improving both the sensitivity and the specificity of what researchers could actually detect. NASA and the European Space Agency have both studied various concepts for exactly this kind of dedicated Enceladus mission over the years, though none has yet secured the kind of firm funding commitment and launch date that would move the idea from serious proposal into active development. It's worth stepping back to appreciate just how much this overall picture has shifted in a relatively short span of time. As recently as the early 2000s, before Cassini ever arrived at Saturn, Enceladus was barely on the radar of astrobiologists at all, a small, unremarkable moon overshadowed by more famous targets like Jupiter's moon Europa. Cassini's unexpected 2005 discovery of the plumes themselves transformed that reputation almost overnight, and every subsequent year of patient, careful reanalysis of the data that single mission collected has continued adding new items to what started as an uncertain, incomplete list of basic habitability requirements. What began as a moon nobody expected much from has become, by the current scientific consensus, one of the most chemically promising ocean worlds anywhere within reach of current spacecraft technology. So what does all of this actually add up to? A small, icy moon has been quietly confirmed, piece by piece over the better part of 2 decades, to contain nearly every basic chemical ingredient scientists consider necessary for life: liquid water, usable chemical energy, organic building blocks, phosphorus, and now sulfur, all measured directly from samples. The moon itself has been continuously spraying into space. There's a version of this story that would have been considerably less interesting to tell, one where a single dramatic announcement claimed everything at once. That's not what actually happened here. And the slower, more careful version is arguably more scientifically convincing, precisely because of that. Each piece of this picture, hydrogen in 2017, hydrogen cyanide and its companion organics in 2023, phosphorus later that same year, and sulfur's modeling-based confirmation more recently still, arrived through a separate team, a separate paper, and a separate round of independent scrutiny built on top of data a single spacecraft finished collecting back in 2017. That kind of gradual, cumulative confirmation, with each new result checked against everything that came before it, is exactly how a genuinely solid scientific case is supposed to be built, even if it makes for a less tidy single headline than a story arriving all at once. That's an extraordinarily rare and complete checklist for any single world beyond Earth. And it's precisely why Enceladus keeps generating fresh headlines years after the spacecraft, responsible for gathering this data, stopped operating entirely. Whether any of that chemistry has actually assembled into something alive remains a genuinely open question, one that will likely require a dedicated future mission built specifically to look for the answer, to finally resolve. If stories like this one, grounded in real published research and honest about the difference between habitable and inhabited, are what you want more of, subscribe to this channel and turn on notifications. Because there's a real chance the next reanalysis of Cassini's archives, or the next dedicated mission proposal, adds the piece of this puzzle everyone's been waiting for. Thanks for watching, and I'll see you in the next one.